And welcome to our review day for Chapter 4. We are going to make a graphic organizer for every chapter that we cover from 4 on. This is a way for us to review. So I've given you a piece of paper. If you're at home, you could find a piece of paper and do the very same thing. We're going to fold this into an organizer. So start with it facing horizontal and fold it once hot dog style. Now we're going to fold it once. And I call this, you need to look here. You don't need to speak, it's a very silent thing. You're going to fold it once, hamburger style. Keep the folded edge on toward the top. Okay, so you've done this so far. Okay, we're then going to take the outer edge, so kind of open it towards you. We're going to take the outer edges and fold them toward the center line. So fold it toward the center line and do it again on the other side so that you have what I call a two-door model. There you go. So it almost looks like a little book. I'm not taking questions right now. Wait till I'm done with the video. Okay, after having done that, two-door, there are two options once you get to this point. But the easiest is probably to put your fingers right in the center and hold it tight and fold the book kind of in half. Okay? And then open it right back up. And you see the lines that formed when you folded it. Okay, so we're ready now to create multiple panels. So we take this, again, you have the folded side facing up. Keep the folded side up. And we're going to just cut. When you make a cut on this graphic organizer, you only cut one rectangle length. You never cross over a vertical line. Okay? So on the inside, you're going to make 2 cuts. And see, we end up with little doors that open. And we'll do it again here. Okay? So we have those doors. The problem now is the top doesn't open because there's a seam on the top. If you slide scissors in like this, you're going to end up cutting the whole door apart. So we don't do it that way. We open up the entire organizer, and we're going to make the final cut here and here. Whoops, there I did make a mess of it. Again, you only cut one rectangle at any time. And then you fold it together. You now have a book with multiple doors. Okay, remember the folded side stays to the top. And now this is going to be the organizer for everything to study in Chapter 4. So we are going to write what you see on the board, Chapter 4, Graphing Linear Equations and Functions, and your name on the front cover right here. So now you have the book with the title and your name on the front. By the time we're done with algebra this year, you will have created 4 through 12, I think, so 9 of these. And they will give you the entire view of Algebra 1. A great resource to study from if you're getting ready for an SAT test or a cumulative test in algebra. Okay, so keep these in a safe place. Okay, when you open up your organizer, there are 4 panels. So each of the chapters will be divided into 4 big topics that we covered during that chapter. And so the first one today for Chapter 4 is graphing linear equations. And the first way we learned how to do it was using a table. So put that on the upper left panel, graphing linear equations using a table. Okay, so whenever we go down underneath the panel, which is what we're about to do, underneath this graphing linear equations using a table, we're going to the next panel. So you're going to write on the back of the panel you just wrote on. And so we're going to put examples and rules and all kinds of information about graphing using a table in this section. The first thing we learned was that we need to put our equations in function form, which just means isolate y. After that, what did we do in order to graph it? You put the equation in function form, and then what did you do? Ronnie? Well, actually, this was before we even did slope-intercept. Cameron? And Brian? Make a table. We just simply made a table. You guys are jumping to slope-intercept, but this was just making tables. Minimum of 3 solutions in case we made a math error, right? We found solutions, which another name for solutions are, begins with a P. We find them on graphs. Points, that's it. So then we could take those and plot them on the graph. After plotting them, they represent only 3 solutions. So to show all solutions, we did what? We drew a line through them, okay? Let's remember what the standard form for linear equations is. Sometimes you just ask this question to write a linear equation in standard form. And so, who can give me the standard form? Ellie. That's actually slope-intercept form. I need standard form linear. Billy?
M equals...
No. Jake?
Y equals X?
You gave me the parent. It is AX plus BY equals C. And we just said that the solution of a linear equation is a point. Go to the next panel down, right across from where we just wrote that, and let's graph y equals 2x plus 2 using a table. So draw a little table in.
Do we open up to this next page?
Okay, so we have chosen 3 nice values to plug in. When you plug in -1, what do you get?
2. Or 0, I mean.
Okay, when you plug in 0, what do you get?
2.
And when you plug in 1, you get
4.
4. So there we have 3 solutions, 3 points, and we are going to graph those now. -1, 0, 0, 2, and 1, 4. So we now have those 3 points graphed, but we were asked to graph this entire equation, so we weren't limited to 3 points. Sometimes they told us just use 3 points, but this time they didn't. So we're going to go ahead and use a straight edge, draw a line through, and show your arrows to go beyond. Okay, so we have used those 2 panels, so we'll open the door one more time and do this final statement. What's the difference between discrete and continuous functions? Okay, discrete, he says, stops. In what way does it look, what does it look like on a graph? You want to say something more? Just individual points. Good. Continuous, though, is
Infinite.
a line, right? A line where the points have been attached and we've sent the arrows off in different directions, okay? So we have discrete versus continuous. We only, rarely do we have discrete, but if you're ever told to simply plot these points using this, domain that's restricted to 3 things or something, then you might make a discrete graph. Okay, and so underneath this section, we're going to include transformations, which we talked a lot about already with the assignment today. And so we can transform a linear equation by applying a rule. We're in the last panel of the first section. Okay? And so if we multiply the equation or we add something to the equation, we can change it. That's what transformations are, changes. So the first type of change is a slide, and a slide is really called what in math, everyone?
Translation.
Good, translation. And what causes a translation? Is it adding or is it multiplying? Adding, good. So here's the rule behind it. You're adding or subtracting from it, from the equation. Good, so the vertical stretch or shrink is when we multiply our slope by something. Vertical stretch or shrink. That means timesing m, multiplying the slope by something. And you know the difference. When we multiply by a number greater than 1, it stretches it. By a number between 0 and 1, it shrinks it. And the final transformation happens when we multiply the slope by a -1. And you get a
Reflection.
reflection, that's it. So if your slope becomes negative, you get a reflection of the parent. Negative m. Different kinds of intercepts. So the second method for graphing was using intercepts. And then the third method, which we'll do in a bit, was using the slope-intercept form. Okay, but we're going to focus on two here. Graphing using intercepts. Putting the second panel, and on the back of where you just wrote, graphing using intercepts, we're putting on the back of that you're finding what you just said, and that is the x and y intercepts. So we made a little plan. Some of you forgot this during the quiz. Finding an x-intercept simply means plugging in what?
0.
For
Y.
y. Good. All you have to do, plug in 0 for y. Finding the y-intercept, all you have to do is
Plug in 0 for X.
plug in 0 for x. Okay? And that gives you 2 points, which is the minimum number you need to graph a line. So you plot them and graph. Okay, so all we're going to do now is graph using x and y intercepts. So you have, this is all we're going to do. Find them and graph. Nothing else underneath this panel. If you want to use more than one rectangle, you could. This is all we're doing here. So graph, find them and graph them.
Plug in 0 to 3, then 0 to
So you say
Y.
2x plus 3 times 0 equals 6. So 2x plus 0 equals 6.
yeah, then you get 3.
Okay, so 2 times 3 would give us 6, so she can jump right to saying that. Okay? How about the other one? Who can give us the y? Jake?
2.
And you did that by plugging in 0 here, right? So let's just show it. 2 times 0 eliminates that. 3 times y gives you 6, so he says y equals 2. There it is. Okay, you have 2 points. If you wanted to use another panel, you could use that, or maybe you could squeeze it in. Y, x. And we find those 2 points. 3, 0, walk 3, fly 0. 0, 2, walk 0, fly 2. And use a straight edge. And there you go. Isn't that nice? I mean, we often want to just use slope-intercept, but this is a very nice way of graphing as well. Okay, we're moving to the third panel, graphing linear equations using slope-intercept form. So what do you think we're going to put underneath this panel? Brian? Good. We're going to actually put the form, y equals mx plus b. And we're going to describe what that is. Okay? And what is m, Cameron? What is m? What is b? The y-intercept. Very good. So put those down. So if you want to graph using this form, we need to start with putting the equation in this form, right? What would you do next? Billy?
After you put it in,
Yep.
then you graph it.
How would you do that?
You put
If you're going to tell somebody, this is the form, now what do you do?
a few numbers, and then you go explain.
What are you going to find here? How do you say it, Stuart? And then where do you go from there? What do you do next, Aiden?
You use the rise over the run of the slope. If it's just one number, it's over 1.
Good, so you use a slope to find the second point. Once you have those 2 points, what can you do? You just draw the line through them, right? And you have it. Graph this using slope-intercept. Okay, so we changed it to slope-intercept form, and now we graph it. We start with, again, what point do we start with? The y-intercept, right. And then we use the slope to find a second point. So your y-intercept is at 2. And the slope is down 2 and positive 3 runs. And you have 2 points and you can graph the line. And the next topic is finding slope. So in this section of using slope-intercept, sometimes we had to find slope. So jot down the equation used to find slope. And tell us what that is, Aiden.
So find the slope.
And we learned in our real world problems that slope is the rate of change. It's a rate. Often with two, you'll see 2 different unit forms and you have the slope. So on the final panel, we want to just talk about the types of slopes that you can find in a linear equation. So if we imagine the parent equation where left to right, you're going up. So everybody show me this with your arms going up. What kind of slope is that?
Positive.
Positive. And now show me with your arms negative slope. So going left to right, we're going down. Show me with your arms undefined slope. Undefined. Very good. It is straight up and down, like you're falling, free falling. And then 0 slope. Good. So on the panel, you're going to show each of those kinds of slopes. Real quick sketch. There's a certain type of line that always passes through the origin, and that kind of line is
Direct
variation. And then we use a special way to name lines, which is called function notation. Okay? Final panel. Okay, the first thing we did was a direct variation. So can you give me the equation, the model for that? It is y equals ax. And a is just a letter that has replaced what letter?
The slope.
Slope letter m, right? It's the only constant in the equation, so it is called the constant of variation. And you might have to answer a question like this. Is this equation direct variation? If it is, name the constant. And the constant is actually -1/2, right? When you subtract 3x and divide by 6. Okay, write a direct variation equation for the graph. There, that graph. So go ahead, draw that and write a direct variation equation for that. So when you write a direct variation equation, if you see those words, you start with the model, right? And the model we said was y equals ax. And so now there's a couple ways you could do this, but one is to, anybody? What could you do? Billy?
Well, you rise and run, so it's 2x equals y.
Okay, so he's just using slope. He said you do rise over run, and from 0, we're going up 2 and over 1. The other thing you could do is substitute the known point in the equation, and this is y, so 2 would equal 1 times the x, and so in other words, a still equals 2 by substitution, and then you write the equation, y equals 2x. We're almost there. Function notation was a way to name a line. And we start with the most common way to name them, and that's f of x. F is for the function. Function x equals mx plus b. And we said that means f of x, right? What did we say we could replace f of x with? Y. So we can actually say this is the same as y equals mx plus b. And so we have one equation coming that is in function notation form. And we simply can graph it and we're done. So here are the kinds of questions you could be asked for a function. Find x if f of x equals 8. Find y if x equals 4, and graph it. Put it down. You should be writing. Okay, so in this first case, we said that when you plug in 8 here, you end up with x equals 2. When you plug in x is 4 right here, for part B, you get 14. Okay? And then finally, when we graph it, we can start with a starting point, 2, and we can use a slope, find a second point, and boom, we have a graph. And now when we compare that to the parent function, who can give me the transformations? Checking out the y-intercept, how does that compare to the parent function? What is the parent y-intercept? 0. This is 2, so the transformation is up 2. What do we call that?
Translation.
Translation, right, this is a translation. And the 3, the slope is 3. How is that a transformation from the parent?
Stretch.
It is a stretch. Good. So you should have that down too.